Okay. So it's a pleasure to welcome Mark to EMC today. I've known Mark, this is Brian, for those of you on the phone. I've known Mark for, I'm going to say 20 years or so, since we were both involved in HPC acquisitions in OAR. Mark has been with NOAA for 35 years, which was something I didn't know. You must love NOAA. So Mark grew up in Buffalo, came out with his family to Colorado, got his undergraduate degree at CU in Denver, and got his master's at CU in Boulder in computational sciences. Mark worked within what is now known as GSD, doing some compiler development and some HPC optimization. And he's leading the HPC section now and has been for about 15 years, where he's focusing on new technologies and some exploratory model development. So all of these topics are wrapped up really well into his seminar today, Advancing U.S. Operational Weather Prediction Capabilities in the Next Decade with Exascale HPC. So thanks, Mark.
Thank you, Brian, and thanks to everyone for coming to hear. This is exciting for me to be here, make the trip out, and to connect in with the operational side and the closer to operations people that are working there. So the topic that I have chosen is to look a decade out and what the challenges are we face. And the decade is useful in terms of having a longer view of the investments that we make in research that will be applied to operations and improving operational prediction. It's weather, not climate, and there's some important distinctions to make there. Imposes more of a restriction on what we can do and some of the challenges we face. All right, so let's see. All right, so I'm going to start off with the strategic plan, because I took a look at this for the Weather Service and found a lot of commonality. This is a strategic plan for 3 years, and it's got three major goals. We share those in the longer term look at some of the research activities. So reduce impacts, certainly we're all focused on making better weather predictions and being able to do a better job with particularly severe weather, which seems to be increasing. Using cutting edge science and technologies to apply to improve our prediction capability. And the third one is people, the investment in people. So, well, I'm not that old, but 1946, that was when computing really got going, especially from the weather side. And weather has always been a driving application for high performance computing. Basically, you see here the NCEP operational forecast skill gradually improving over a period of time. From the 1950s to today, the resolution of the models have grown from 300 kilometers roughly in the 80s to close to 15 kilometers today. I guess with the new FV3 GFS to be implemented will be there. And also growth in the number of CPUs it requires to run it. So in the old days it was the vector processors with a couple of them, and they were very powerful. Today we have commercial technology, but lots of cores that are required in the order of about 10,000. Basically, you look at the operational models today, we've got global and regional. We certainly have other smaller ones, but the general trend here is you need the global one to initialize the regional models. So it's very important. It runs out for a long period of time, 16 days, and the regional ones for less than that. Basically, the constraint is HPC. We would like to run at higher resolution, but we lack the HPC resources to do it. So we make choices, and in order to get to high resolution, we run at smaller domains, and they're used for shorter forecasts. So the takeaway here is we are making choices with the models that we run, but it's certainly we would like to have higher resolution global models, and that's what the focus of my investigation has been, is how do we advance our global prediction capability to cloud permitting scales. 3 kilometer is the jump that we would face in going from the current resolutions of up to 10 kilometer we have to go to 3 kilometer to overcome some of the issues and instabilities with parameterization or not. But there are other choices, and certainly an improved weather prediction is a combination often between going to higher model resolution, increasing the complexity of the model by including more components, or more ensemble members to look at improving predictability, probability, I'm sorry. So in terms of the model complexity, a lot of what we're doing and proposing to do starts to look more and more like more of the climate system or the full Earth system. There's an awful lot of complexity there, and we certainly can't go there because of the limitations in computing. So the limitations in computing has caught the attention of the Earth System Prediction Capability HPC Working Group. In 2016, we began looking very seriously at the limitations we saw, basically in the effect of the processor speeds flattening out, that they were not getting any faster, and we had problems with how do we advance our model prediction capabilities with severe limitations in what the processors could do. So this was a joint group, NOAA, NASA, the DOE, DOD, Navy, and NCAR that were involved. We have monthly discussions about HPC challenges, limitations for weather and climate. What we have seen and others have is that the new architectures for HPC are going in the wrong direction. We're getting less and less capability out of them for our Earth system applications. NWP applications average less than 2% of peak performance. So some of the conversation we've had is how to get the vendors to pay attention to us so that we can get chips that are more capable of delivering performance for the applications that we care about. And the vendors have listened with a sympathetic ear, but they have been less willing to go down this road because they're driven more by the economics of the market. And so a lot of it has been increasing processor capability, but we're stuck with using what we can with the processors that they give us. There's been a position paper that was written in 2017 about our concerns, and it's gotten some traction with people in industry as well as the scientific community. But I think that it's a challenge for us is that while we're asking the vendors to improve the chips and the systems to become more efficient, we also have to look at how the applications might need to be adapted in order to use the capabilities that we see that are coming in the future for us. So in terms of processor technologies, there are a lot of vendors out there, and this is good. This creates a competitive situation for us. There's CPUs, there's GPUs, there's TPUs, these are tensor processing units, FPGAs, which are programmable chips, and new types of low energy processors like ARM. It's a lot of diversity. There tends to be a lot of cores and an increasing number of cores as these new chips and generations of chips come out. So now on a processor we can expect to have tens to thousands of processing cores on a single socket. And typically the processors are packaged 2 to a node, so it's a dual socket system. It's the burden on the compiler to provide performance, portability, and interoperability that allow our applications to be able to run on these different types of architectures so we don't pin ourselves to any one vendor and lose the competitiveness and the advantage that we have in being able to choose based on price. As I said, dual socket is the standard for CPUs today in terms of compute nodes. But the nodes themselves, if you look ahead, are getting increasingly complex with more processors. More sockets per node is an expected thing, with lots more memory available on the CPU side. And on the GPU side, there's these complex chips that are now being offered that offer enormous amounts of compute capability with nearly 100,000 cores on a chip. So 80,000 cores for the current GPU NVIDIA DGX2 system today. And these typically are packaged onto a node with a CPU host. That's the way that GPUs work today, is you have to go through the CPU. but there's been improvements in how fast you can get information from the CPU to the GPU, and that is found here on this DOE Summit machine. The architecture for the Summit node is 2 Power 9 CPUs and then 6 attached GPUs for this, and they've been put this together with 4,600 nodes, 27,000 GPUs on this Summit system. So that's an example of where at least computing, HPC in particular, is going. There are other systems of equal scale that have chosen different ways to assemble, but this is the trend. So in terms of application performance on a single node, there's been lots of work here to compare how one vendor does over another. This is useful in being able to push the vendors to support us more. Here you see this is the MPAS model that was developed at NCAR, 120 kilometer grid, and then comparisons between the CPU and GPU chips. So this is a dual socket CPU Broadwell versus a Pascal GPU or a Volta GPU. Volta is in gray, Pascal is in orange, and the CPU is in blue. Lower is better in these numbers. You can see that the GPU is 2 to 3 times faster than the CPU for the MPAS model on a single node. This code that MPAS has is directive-based and it's performance portable. So it's the same code base that's used to run on the CPU and the GPU.
Is that the complete MPAS prediction model with physics and all
Yes,
the
it
bells and
is.
whistles?
Yes, it is. So they've done a nice job here in being able to pull the entire model to run on the GPU. They have taken the advantage of the nodes that have fast copies between the CPU and GPU with new technology. And so that's why some of the physics actually doesn't run on the GPU, but it can be moved very quickly between the CPU and the GPU. Non-uniform icosahedral grid that's here, it allows for stretching to go to finer resolution in some areas and coarser resolution in others. With the FE3, my group did a fair amount of work on trying to adapt the FE3 for GPUs. This was work that went on in the last 2 or 3 years. We spent about a year and a half looking at this and really got disappointing results. This was really a huge disappointment to me, was the thought we could apply some of the work that I had done on other models to be able to show performance benefit here. But it's about, there's some problems with FE3 that have been hard to overcome. There's limited exposure to parallelism in the FE3 model that are needed for the GPU. And the non-uniform cube sphere grid imposes some difficulties, inefficiencies in FE3 performance on the GPU. The corners and edges calculations are pervasive in the code, and it really drags down the performance. So there are efforts by other groups today. We're in contact with people from the Swiss Supercomputing Center, Medio Swiss, to rewrite the FE3 and write it in another language for their purposes to demonstrate that they can get beyond this using a suite of tools that they have available and demonstrate value for running the FE3 on both the CPU and GPU.
Excuse me, what exactly is the problem with parallelization? Is it the 6 phases paradigm that actually is forcing later the composition or something else?
No, so in the case of the FE3, the challenges are that parallelism is in the FE3 is at a fairly high level. It's applied in the CPU code. So we have a lot of 2D arrays down inside of the FE3 routines for shallow water, for instance,
so
and so on.
how the code is written, essentially.
Yes, that's right. Yeah, the way the parallelism is laid out is a benefit for the CPU, but a problem for the GPU. That we need to lay out parallelism a different way, and when we do that, we lose the benefit for the that the CPU had. Performance gets worse in order to get improved performance on the GPU. So portability is a challenge as well. So you can have all this power on a single node, but you still have to communicate. And large systems use an interconnect, and the interconnect is relatively fast, but the nodes are getting faster and more capable than the interconnect is able to deliver communications. And in addition, from the application side, we have MPI communications, which has its own inefficiencies. It's a relatively heavyweight process. So when you look at it in the aggregate, scalability is going to continue to be a big challenge for us in getting good application performance for our applications. FE3 and others have this problem. So you can have, in this case, I show a dual socket CPU, but as I showed earlier, the technology is going towards more and more powerful CPU and GPU nodes, and that will put more of a challenge on the interconnect's ability to be able to communicate from one node to another. This has caught the attention of the Europeans. They designed a whole program around this called the Scalability Program. It started in 2014 to look at the problems with scalability for the applications. In particular, their driving application has been the IFS. And you see here are some plots that show the relative performance of the IFS and other models. And the numbers don't look good when you compare it to what an operational requirement would be. So the IFS, they've done some work to run a non-hydrostatic version of the IFS as well as hydrostatic at 1 kilometer resolution. And it runs at about 31 forecast days per day. If you translate that into how we look at it from operations, which is using 8 minutes per forecast day, that would translate into a requirement of 180 forecast days per day. So we're about 6 times short of what would be needed to run this IFS if we had perfect scaling in the numbers that we show here. The similar is true for the ICON model. This is in work that was done for the Diamond project. They meet every couple of years to look at how well can we get our models to run at very high resolution. Their interest is in climate with some nods towards weather prediction, but there's clearly problems here. For a 2.5 kilometer ICON model, it runs about 13 forecast days per day. So if you were to do the math in terms of the number of computing resources, it would be substantial, on the order of 400,000 to 500,000 compute cores to be able to run in a perfect scenario for these models to meet an operational requirement of 8 minutes per forecast day. For the IFS, they noted that 75% of the time in the IFS, which does global communications, is spent in doing inter-process communications. So as I said, so now FE3 participated in the Diamond project. S.J. Lin provided some of the projections for the FE3, and you can see here in the table 13 kilometer resolution, which is C768 with 63 levels, all the way up to a 3.25 kilometer resolution with 91 levels. And his estimate for this, assuming perfect scaling, was that it would require 240,000 compute cores to run and produce a forecast, 10-day forecast in less than 100 minutes. Well, I took this and decided that the best thing to do was to get some more real numbers on this, knowing that we don't have performance improvements like this. It's not perfect. We know that there's challenges, inefficiencies that...
Next slide.
Yeah. There we go. All right, so I took the close to operational version. It's not the current one today, but it's probably a year old. Made some runs to see how well we do with real numbers and real extrapolations that were based on where it is today. So what you see here for the 28 and 13 kilometer, you can see at least some sense of scaling here, and then that was applied in weak scaling to get to 3.25 kilometer resolution. So here the requirement is a 10-day forecast would need to be produced in 4,500 seconds, or 5 days in 2,250 seconds. And so basically this table shows that a doubling of resolution would be maintaining the same workload per compute node we would have 4 times the compute resources. So you can see 4 times the number of nodes going from 64 to 256 all the way up to 4,096 nodes, which is 98,000 cores. And the total time to run that was estimated to be 5,800 seconds, so much too slow for an operational requirement. So we use strong scaling to overcome this, is to apply less work per compute node in order to reduce the amount of runtime. And here you can see the layout at the top, which is per MPI rank is 48 by 48, reducing to 24 by 24, with a total number of compute cores required to run FE3 would be 393,000 cores to meet an operational requirement for the FE3. This is an estimate, and we're doing work to try and get the 3 kilometer running. We've been unable to do that, and that's work to be done. So one thing of note is 30% of the runtime is for inter-process communications. That's a concern, and so we would look at how can we improve capability there.
So do I compare that to the 75% that you showed?
Yes, you can.
Side?
Yes, that's right.
So
and this is why the IFS has had to look more seriously at other modeling approaches, because communications is dominating. While the IFS is very efficient on a computational standpoint, it has problems in communication. So looking at FE3 a little more in terms of scaling efficiency, this was a bit of a surprise to me. This is efficiency where 1 represents perfect efficiency as we go from 32 compute nodes up to 256. So in computation, where you would degrade is if you have issues in the code or the algorithm with efficiency with parallelism, the algorithms are inefficient, or the grid itself leads to areas where parallelism is not available. You're running perhaps scalar operations. And this is where the corners and edges of a cube sphere come into play, and we're quantifying exactly what the impact is there. In terms of communication, the frequency of communications, the amount of data being communicated, and how well you can overlap communications with computation is where you see we're not doing so well here with less than, well, close to 20% efficiency as you get out to finer scales.
So, excuse me, just your estimate. If you replaced a mnemonic cube with a UJ cube that doesn't require any interventions on the corner, on the edges actually, how much will it improve performance?
Well, so early on when I saw these results, I had some back and forth with SJ about having a uniform grid instead. And there's linkages between the choices you make in the algorithm and the way that the grid is that represents those calculations. So he said basically that won't work, that we can't have some sort of uniform grid.
I'm talking about cube sphere where you have continuous transition of the coordinates across edges.
If you could treat them identically,
yes,
there could be a big improvement.
Yes, there is nothing, you do nothing computationally there.
Yeah.
There is a large curvature, relatively large curvature, so you have to think how to solve that numerically, which sometimes could be difficult, but you have to think to solve that.
Yeah.
No computational effort.
So I think our step right now is to quantify how much time is spent in these corners and edges, so we get a sense for the problem that we're up against.
Yeah, that would be very useful.
Yeah. So summary on the computational issues. Traditional computing is not sufficient to run an existing global operational model at cloud permitting or finer scales. Existing operational models. So these are ones that are legacy, they have a lot of investment, they tend to be focused on compute, CPU, computational performance in the CPU, ICON, IFS, and FE3 are all symptomatic of the challenges that we face in running at fine scales. GPU processors can help if we can use them. There are many others that have seen 2 to 3x performance improvements with GPUs, so there's at least some possibility there. Scalability remains a big concern here for us in how we advance capability. Now I'm going to turn to data because if you can produce all this information with a high resolution model, you still have to deal with the data. And it shows up in a lot of areas in our prediction system. Can only be useful if it's used. We've got observations, assimilation, prediction, output, distribution, and dissemination of information to end users. So observations, we have more data than we can use. We've got new generation satellites and polar and geosynchronous. We've got new CubeSats that are available going up. Nanosats are out there. We've got huge amounts of observations that are ground-based, and we're dealing with those fairly well, but I would say that the satellite data and remote sense data is a lot of potential that's untapped. And so if we had better ways of using this information, the belief is that we'd have better assimilation and prediction. There's also tremendous potential in the future with instruments being put on autos, cell phones, sensors, and others. So these are, as we look further out, we know that there's a lot of additional information and our system is unable to handle it as we have it today. So for instance, the geostationary satellites, the GOES-15 data, we're only using about 1% of the data. The new generation satellite now, geostationary satellite, has scans every 15 minutes, opposed to scans every 3 hours, higher precision, more spectral bands, more visible bands, and nest capability. But we're unable to use the data that we had in the GOES-15, so we're going to have to work a lot harder to use the capabilities available in our current generation GOES. So in data assimilation, we use a technique called thinning, which is to reduce the amount of data that goes into our assimilation system simply because we don't have enough processing capability to handle it. So we take every 100th point, 1% of the data is 100th point. Here I show a little bit graphically what that looks like is we have points and then we apply that to the model background state. We have to do an estimation for model error and observation error. We have to interpolate the data that we have observed with the grid itself and how it's used in the assimilation. And then we have to adjust points that are nearby. This is the assimilation process. So if you have a GOES-15 that runs at 4-kilometer resolution and you're only able to use every 100th point, then you're using data every 40 kilometers. A 40-kilometer grid square would be represented by a single observation in the GOES-15. So it's underutilized, and this is a concern. Assimilation is both ensemble-based as well as variational, and there's challenges computationally in both. If you run lots of ensemble members, you've got I/O problems. We can only afford today to run tens of members when in fact in order to get a good distribution we need to run much more. In terms of 4D variational assimilation, it's higher accuracy, but you need to have a tangent linear adjoint, they need to be maintained, and 4D VAR runs slower. So we have some challenges here to look at how we improve our assimilation capabilities. Hybrid appears to be the best way that many groups are going, which is a combination of ensemble and variational techniques. In terms of distributing the data, there's diverse user requirements, global, regional, local requirements. The way that we distribute data is more or less through the NOAA network, where everyone gets the same data. So what's happening in New England doesn't have a lot of use for what's happening in Hawaii, and yet we get a lot of the same data. We're also very restricted. Now we're saturated with how much data we can distribute across the NOAA network. So that's a concern. You look at, if we go to 3-kilometer resolution from 14 kilometer, you can see the numbers here. For a single 3D variable, looking at model output, it's about 21 times the increase in the number of grid cells for 3-kilometer over 14 kilometer. And if you write your output today, 10 model fields, 6 hourly output for a 10-day forecast is about 400 gigabytes per run. 3-kilometer with 10 fields, 3 hourly output, and 10-day forecast is about 52 times more information. We we already have problems transmitting the information we have today. So it's more serious challenges here. So the state of operational NWP today, exceedingly difficult, as I said, to run operational 3 kilometer. From HPC, no expected increase in processing speed, limited increase in memory speed, parallelism and scalability limitations, and we still have the operational time to solution constraints. On the data side, there's too much data to process, too many observations to use, and it's too large to distribute. Pretty grim. Brian?
We're doing great.
Yeah. I know this is a little depressing, but I don't ever, the reason I put this up is this is a 10-year sort of look at how do we get smarter about what we do so we're positioned to make improvements in the future. But this is grim, and it suggests some fairly big challenges. Where do we go? Well, we have to look at the entire system from the data to the stakeholders, the end users, utilize new technologies, improve our prediction models, able to use more compute capability, better data handling, and manage the complexity of the software. So, supercomputing is changing. We've relied on HPC for a long time, and it's served us well, but there are limitations with how far HPC can take us. Fortunately, there has been a technology convergence. We've heard a lot about machine learning. There's opportunities there. There's big data opportunities as well in terms of analytics and other things that we can do to more intelligently handle the data that we have. So I will look at how some of these new technologies are enabling research that will give hope for some of the challenges we face in our operational prediction. Number one, improve model performance. This is obvious. We need to evaluate our models to look at both scientific accuracy that we can achieve and computational efficiency that we can get. And this is going out to very fine scales, to 3 or 1 kilometer resolution in developing small models that can look at the algorithms, can look at the grids, can look at time integration, and see what it is that in combination is going to give us the most bang for the buck. We can incorporate parallelism in our models at all levels. Right now we've had models that are designed where we impose parallelism where we can, but we're going to have to increase that. Minimize inter-process communications and improve I/O capabilities. All of this may require re-architecting and rewriting our prediction models. So you can see here a graphic which is a three-dimensional space in which we look at scientific accuracy, computational efficiency, and software design. So what are the best models and approaches for emerging HPC? We need to look seriously at this in terms of the algorithms, the type of grid, the time step, the physics, and so on. There's been a lot of work done with the time step. This could be the biggest thing that we could do to improve our parallelism and performance, is if we can take larger time steps using semi-implicit schemes, for example, then we would have less communications. We need to look at the combination of semi-implicit time step, for instance, and the role of the formulations, finite volume, finite element, or spectral element.
Excuse me, how you said semi-implicit approach assumes implicit handling of adjustment terms. That means actually global operators, meaning more communications. That's the reason that we are not going to semi-Lagrangian schemes. At one point we gave up that route precisely because of semi-implicit approach.
Yeah, now I'm not qualified to answer that as a computational scientist. However, there is some work that's been done to look at different time integration strategies with different model approaches. And there's always challenges.
There are exponential integrators that look very promising, but and there are some other things. But classical semi-implicit, that means that we are solving implicit equations that require global operations. That means lot of communications.
Yeah, I think this would be something to take up with some of my colleagues.
I'm sorry, I'm talking.
That's all right. So we have begun development of what are called dwarfs. This is a term borrowed from the Europeans, and prior to that was one that appeared in the 70s to describe small computational kernels to look at very specific things. So in this case, this is an application framework to simplify development in order to evaluate efficiency versus accuracy of various approaches. The two approaches we're looking at are finite volume variations of icosahedral finite volume and spectral element, CG and DG methods. Right now, we're using C++ objects to define communications, grid, discretization, time stepping, and so on. And we're focusing on advection first because we can look at communications, MPI communications, and scaling out to 1 to 3 kilometer grids with different architectures. So there's a lot of work in here, and so some of this is going to be making some choices and seeing where it takes us in this development. This has been going on for a year and a half. This, as I said, it borrows from the Europeans, and they are doing this with extracting from their existing models and exploring alternative numerical algorithms to get around the scalability problems that they see. They're also looking at different modeling approaches in the IFS, knowing the limitations that they face. We're also looking at the evaluation of the age-old debate about the grid staggering. A grid is unstaggered, all the information is stored at the cell center versus C grid staggering. And it's not just to determine whether one is more accurate than the other, but to also evaluate what the computational cost of this is, and being able to quantify this in a way to suggest, well, if you're more accurate with one approach, then you can do higher resolution with that same approach and perhaps overcome what might be a scientific limitation of that. We don't know, and a paper is coming out that describes and goes beyond some of the work that was done in the NICAM and the MPAS for the A grid and C grid calculation models. So looking at advection, this is work that we did to evaluate and quantify performance. Here what you see is a model, in contrast to what I showed with a bigger model, which was the FE3. So it's only a restricted area, it's dynamics only, but it's showing very good compute capability. Still the degradation you see in communications here in the red, but the overall runtime, the total runtime in green, is not very affected by communication. So this suggests that the communications we've been successful with minimal frequency of communications, low data volume, and overlapping. We've been good. So this is a sort of target. Now this is a naive example, but this is what we're looking for in terms of evaluation of how well we can design models that achieve good computational performance and scaling. Physics. 2/3 of the model code, source code, is the physics, convection, radiation, and so on. It's computationally expensive. There's less parallelism available in physics than there is in dynamics. And also has good potential for machine learning, deep learning, to have replace some of the parameterizations in the physics with machine learned algorithms. This is all very new, so we don't know where this is going to go, but we have to look at this in order to determine whether this is a viable path for us. We can also combine physics and dynamics. Some of this work has gone on at GFDL, and other modeling groups are exploring this as well. Number 2, how am I doing on time?
We have at
Time?
1 o'clock.
Okay. Improve data assimilation performance. Data assimilation may be an even bigger opportunity to improve our prediction than the model itself. Again, scientific accuracy, computational efficiency, and software design. So JEDI, we've been following and we've been working with this team. They have a huge effort, which has a lot of modeling groups involved. And you can see here FE3, the MPAS, Neptune, the ELFRIC from UK Met Office, and MOM6 are participants as well as others. So this is quite comprehensive, and it looks like a good way forward for us in assimilation to leverage and use the capabilities of JEDI. They're less focused on performance today, and I think that we're going to have to look in there and figure out what opportunities there are to improve the capabilities within the JEDI system. So one of the things I mentioned about the thinning, we've begun looking at intelligent thinning, which is to be able to select more observations in one area where there's severe weather and less over another. And so this can be done through the ensemble, the uncertainty in the ensemble. Can also be done with machine learning, feature recognition for specific areas of the atmosphere that look more useful for the assimilation system. And so in feature detection here, I don't think this will work, but if this will show. Actually, I won't try here in the interest of time. To identify typhoons from satellite data, this is a very early experiment of can we get accuracy, and we can. And will that accuracy translate into changes or improvements for assimilation? Well, probably not for typhoons, because those are pretty easy to pick out, and the assimilation certainly isn't going to miss out on that. But this is work still going on. Takes about 6 years of data for training for this machine learning, and the GPUs provide a huge benefit for this. 11 hours on the CPU takes 3 minutes on the GPU. For inference, or when you've trained the algorithm, there's not so much of a benefit here, but it's still useful to know that yes, you can run in a second on the CPU for this feature detection versus 20 times smaller than that. All right, soil moisture. So we're using machine learning to look at soil moisture. Can we improve the estimation of soil moisture and be able to apply that to our assimilation for improved prediction, improved assimilation? So this work is going on, and we'll see probably in about a year some idea about this applied to the HER, how much of an improvement we can get here. Number 3, getting data to end users. So the data is too big to move. I've quantified that some. We've got systems and networks that are incapable of moving the data that we need. So it's too big to move. We need to keep it in one place. The possibility of using cloud for this, at least, is one we need to look at. I think it's got good foundation capabilities that allow you to have lots of accesses into large data stores. Is certainly a good direction. So we co-locate the HPC resources and the data, and then provide on-demand access to the data as needed. And so it isn't transferring huge grids around, it's providing information, insights, visualization, and potentially grids, so real model grids, but a subset of the grids that a model would produce. So this is a sort of tailored technique, I think, that would help allow us to have very high resolution models and be able to distribute only what's needed to the end users.
So this is an interesting slide in the context of having redundant operational systems.
Yes.
I don't know that you can consistently have HPC and data co-located
We don't.
all the time.
Yeah.
Okay.
We don't, and yeah, we tend to move stuff around. You think about observations going into such a system. There's a lot of challenges here too, but this is certainly an opportunity. And I think about challenges like security and NOAA policies, which are emerging and evolving, but there's still a lot of things. So I think in some of the work that we're looking at here is to have internal cloud capabilities first and demonstrate the value of this sort of approach to get very high resolution data sets and then quantify how fast you can get to the information that you need in delivery to end users. This is at least a research direction that we have chosen to do. 5G and edge computing. Edge computing is kind of a new term that's come out of late. You could think of it as computing that's local. I show here on the left a map of the Chicago area with a local cloud capability. Huge amounts of data that's available locally, certainly with 5G. This is coming. We've got smart grids, we've got sensors, we've got small devices that are going to record information. We've got cars and planes and other things. All of this is very high resolution local data, and we can have compute capability locally that does a lot of the work for us and transfer only a subset of that information to your global clouds. This is an opportunity with 5G coming. We know there's enormous amounts of data there. We can't use all of it, but we can figure out how to use intelligently what we need. Number 4, improve software architecture in our development process. This is an enormous challenge when we see that anytime we need to move models around, when we need to work to get models to be modified, to get researchers to begin using it, to reach out to the research community. This is a challenge in the source code, the scripts, how we validate to make sure changes we've made are correct, and documentation. I know you all have been heavy in this with the FE3 GFS. We have on the other side goals to have our modeling systems where we have tremendous investment to be able to support portability, high performance, maintainability, and extensibility. This suggests more of an architectural approach in how we design our software and an engineering approach to how we maintain it in a process that includes design, development, test, commit, and refactor. Refactor is something that often falls by the wayside, but I think as we see models continue to evolve and more requirements, we need to have the time and the ability to go in and rework and make more substantive changes where required. Otherwise, we just get dragged down in the ability to get our models to perform and to meet requirements that are coming. So again, the JEDI system is a demonstration of how this can be done better. I have observed how the JEDI group is working with different modeling groups, and they have this architecture from the very beginning was designed where the modeling layer you see at the top, FMS plus FP3 being one of them, written in Fortran. There's classes that allow you to define the geometry used in the model, the fields, the state, and so on, support for assimilation. And then the JEDI layer, which is model agnostic with object-oriented design and different capabilities within the assimilation system. This group has been very effective, I think, in being able to satisfy the different modeling groups and have a process that is, I think, very good for the scope of development that they have. So, in conclusion, good, I'm just about on time here. Major challenges in advancing our prediction capabilities in modeling, computing, data handling, and software. New technologies and approaches are needed to move beyond our current capabilities. Traditional HPC is not sufficient anymore. I never thought I would actually say that, but we're reaching really the end of that alone being sufficient for us, and I think a lot of that's driven by the fact that the processors are not getting faster, that it's forcing us to look at different technologies and ways in which we solve problems. Our laboratory has begun doing exploratory development, machine learning, cloud computing, GPU computing, work to quantify the choices that we have in the science that we develop and how efficient they are computationally with current hardware as well as emerging hardware. And we've begun looking at tools to deliver this information, insights, pixels, and grids to end users. How can we do this better and manage the enormous amount of data that we have? Now, this is mimicked by what's happening in Europe. It's quite impressive how comprehensive the work is that's been going on at ECMWF and others in Europe, looking at all the same things that I've just presented to you in terms of the algorithms, the challenges in data, the challenges in I/O, assimilation. All of these things are being done at a big investment with more to come that are looking like they're even more comprehensive. So a lot of projects here, a lot of activity. In a way, we're trying to hang on to the coattails of what they're doing in Europe to try and keep up in how we advance our predictive capabilities for the future. So final thoughts. Common goal. This is a little bit like what ECMWF has in their motto, a strength of a common goal, which is we have operations and research And we have opportunities here. There's requirements in operations that we work more in the near term, and can we take advantage of more of the longer term research as we go forward? I think we can, and this is partly why I wanted to come out here. I believe that we have a strong commitment to FV3 GFS. Certainly it's going to serve us well for a period of time, but we need to continue investing in longer term research that moves us beyond the capabilities that we have today. FV3, I've got 3 people that are working on the performance issues that we have, working on adapting for the GPU, using containerization and cloud. Those are work that people are doing now, and improving the I/O capabilities of NetCDF. There's a presentation next week, 2 weeks from now, about some of that, quantifying some of the improvements we can get with new NetCDF work that's going on. I also think that needs to be a sustained commitment to do longer term research that will enable operational prediction capabilities in the future. That we need to do that too, investing in our lab and other laboratories in the modeling, the assimilation, big data, cloud, AI, and new HPC. And that's a lot of what I've suggested in the work that we have done so far within the lab, and I think that commitment needs to be sustained. So that's all I have. Thank you.
So I have a couple of questions. If you can go back to your slide where you had the FV3 cube, it's way up front.
Way back.
Mm-hmm.
Maybe you can just do the escape and
Oh, I'm almost there. Oh, sorry.
find it.
One of these or,
No, you actually had the cube and the vertices and the edges and stuff
Excuse me.
oh,
shown.
Which one is?
Maybe
It's
10?
10.
10.
thank you. That one, yeah. Ah, so fast. I don't like these fast
Oh,
mouse.
sorry.
All right.
Okay, so you said the issues are that computation is different at the edges and the vertices. Of course, you have only 8 vertices, no matter what your mesh size is, and as you refine your mesh, the amount of computation or space taken up by edges and their halos gets smaller. So are you seeing anything better because there's more of the internal points to each
so-
of the sides as you refine the mesh, and you're seeing any kind of improvement from that?
Not yet, although it's actually counter to what you said, if I understood it correctly, is that what you really want to look at is the ratio of the number of points that are internal to the number of points that are the edge. And so as you go to finer scales and you have a smaller number of points per MPI process, the ratio of edge and corner points grows. It gets worse. And we haven't quantified that yet. In fact, the entire, the effect of the edges and corners, we don't know if it's 20% or, because getting measurements in there is tricky for being able to do this over the all of the places. As I said, it's pervasive. It shows up in a lot of routines, the edges and corners, and special treatment that shows you're stepping into, it's not just the edge point, but it's 3 points in to the edges where that is. Yeah.
So you never mentioned, but I'm sure you're looking capabilities of quantum computing. At the moment, we know they are limited to very specific applications. But I heard that there is research going on to generalize that, and so did you look into
There
that?
is,
Do you have any thoughts?
yeah, so we continue to see over the horizon opportunities like that. We have seen the same thing with FPGAs as well, is that they always seem to be a little further out than it's reasonable for us to begin, but certainly that particular one has great potential. Whether we can apply it to our really complex
I mean, I saw
models, I
that
don't
people
know.
in computational science are playing with algorithms and software and whatnot, even though technological capability is still not there.
Yeah,
And
yeah, no,
just,
that's
did
right.
you hear that someone in our discipline started playing with those ideas, thinking how we could run our models if that was...
Not yet. No, I haven't seen anything yet. Is anybody on the line?
Yeah, it's just a question. There's a question from online. Yeah, could you? I couldn't make it on the screen. From South. Please mute us.
Yeah, so this is Bill
Here.
Penta. Mark,
Yeah.
Yep.
so I appreciate the presentation. I have a question. One of your last points was talking about architecture and software engineering. And so is your group tied into the UFS different working groups relevant to those aspects?
My group directly has not. There was a working group that was, I think it was formed a year or so ago, but it seems like it had fallen off in terms of anyone organized or discussions. It could be, that might have been a software infrastructure group as opposed to the architecture.
Okay, so does your group interact with other groups and projects within the agency doing similar type work?
Well, we've struggled with, so the software infrastructure and architecture is, I've had some contact with DOE in how we do software development and how we manage software complexity, but there hasn't been any kind of sustained group that's been discussing this, especially in NOAA. I've seen very little.
Okay, thank you.
Yeah, Robert Moorhead, Mr. Robert Moorhead. You sent a message to the Mary Hat. Could you send a message to everybody? Maybe that may help. Maybe I can copy.
Brian, did you?
Yeah, so while we're doing that, I have a few questions, so I'll do one and then see if anybody else has a question. We'll get to that one. So you mentioned a variety of programming languages in your discussion. My understanding is that Fortran is still producing the fastest code amongst the programming languages, but as far as I know, we're not growing very many Fortran programmers. So have you guys thought about how we're going to make this kind of transition both on the performance side and on the software engineering capacity side?
You know, it's a tough one because there's so much investment in what our current capabilities are. And there is really, I don't see any, there's no performant reason to choose a different language. I don't think they add any value from a performance standpoint. They can add value from a design standpoint, that we can have capabilities and ways of handling different types of development. That's where object-oriented approaches can help us to some degree. We can't overdo it on that the computational pieces need to be simple and clean, or they'll lose performance. And performance is king for everything that we do. It's so important that we do this right. So in terms of not enough Fortran people out there, I don't have a good answer other than to say that people, it's easy, relatively easy to learn Fortran if you know high-level languages. Similarly, it's relatively easy to learn another high-level language than Fortran. Is that if you keep it simple, they're fairly straightforward and similar. But that's a challenge. When you go to universities and tell them you want to hire a Fortran programmer, they all wonder which generation you came from.
And the fact that you've got so much legacy Fortran out there that, you know, it just even if you were a great programmer and just rewrote everything, checking that stuff out is a challenge.
Excuse me, someone's breathing to the microphone. Could you mute yourself?
Or we're calling the police.
I think there is one question from the Robert Moorhead, Mr. Robert Moorhead. That's in procuring it. I is missing. Sorry.
Oh, in procuring HPC resources, one can choose the communications network to some extent. Yeah. Yeah, this is a tricky one, is that we know that communications is a weak point. We don't know how weak it is. And, you know, some of it's imposed by the algorithms that we choose. And I think there's probably more of an opportunity there. But when we look at procurements like large systems, like the DOE Summit machine, you see relatively how small the interconnect is, and what a concern that is. But we haven't quantified it enough to know how much do we actually need. Could we have a requirement for what sort of communications we need? Because it's not just the speed of the interconnect, but it's also the MPI communications and the overhead there, and the application and how well it's doing communications. Is it small messages? Can we aggregate into big messages? And what are the ability to hide that? So I guess I don't have a good answer to that.
So I had always associated that low percentage of peak with the low computational intensity of the codes and the nature of the problem that we have, which was actually one of my other questions. So you could do single core studies that show we just reference memory too much on traditional architectures and don't do anything, don't do enough with it.
Yeah.
So if we're going to address the percentage of peak problem, does that demand a re-architecting of the hardware based on the nature of the equations that we need to solve?
I think we'd have to get the vendors to, put more traction into that, which is, better memory performance. And that's the nature of the discussions that we've had with vendors, is will they do that? Intel has been more willing to do that, improve their memory performance. There's limits there. I think we can expect a 2 times performance improvement in memory in the fairly near term with the Intel processors. But I think that it's still going to be, a challenge in the way that we write our codes. Is can we have better computational intensity, which is the number of memory accesses per computational activity. And I think that requires revisiting the algorithms and looking at the way that we combine science. One of the fairly early research activities we're going to do from advection is to look at convection and advection running together, so that we have an opportunity to combine computational work at the same time.
So this the last thing you talked about, combining different processes and doing them at the same time, it's really going away from the paradigm where we are trying to modularize and separate.
That is the tension that we have, is that for convenience we like to modularize to allow independent groups to work independently and then combine them with some sort of infrastructure. And I think we have to, it's a tricky thing to figure out to what degree do we benefit from modularizing versus combining. And I don't have an answer to, how we address that. But there is the notion, and it's starting to break down, is that physics and dynamics need to work more together than they do today. And that imposes then, that breaks down some of the separation that we've enjoyed, I would say, so far today.
David Macaron, he wants to ask some question.
Hey, Mark, good talk again. This is Dave McCarran from ESPC. So I may have missed it, but you said as the commodity-based computing kind of comes to an end with the end of Moore's Law, there's going to need to be this change to more problem-based computing. What time frame do you think that will be in? And the second part of the question is, how do you think the HPE buyout of Cray will affect the industry?
I don't have a wand on that one. I am encouraged, at least in Cray has been presenting itself. in a more comprehensive way for earth sciences. I think they have, they're more aware, I think, than I've ever seen them in how they discuss challenges that are computing as well as data, but I don't know how HPE is going to affect them. There's been cases in the past where the buyer didn't understand fully what they were getting into, and Cray has maneuvered its way through several of those. So I just don't know at this point. What was your second question?
When will the changeover be from commodity-based boxes to more purpose-built compute? As law collapse.
It's hard to envision. The fabs are so expensive now, and the complexity going to very fine scales. So I think they're doing 7 nanometer now, and the fact that they have enormous fabs to do this it's just hard to imagine that we'll very easily get traction. I think the closest thing we can do is FPGAs. That might be an avenue for us, but it's hard to see that the vendors are going to want to invest for a relatively small community unless we can convince them that the community is much larger. And I think that's a goal for us to work with NSCI or its, I guess the new one, NSCI is being replaced. But from a strategic standpoint, can we get the attention and say that geosciences is a strategic and important enough that investment can be done to drive vendors to work in this area?
Any more question?
One more. It's on your last slide, and it's not a question so much as a comment that I think there are near-term things that we need to do from an operational perspective. But I don't want to put off the near-term things that we need to do from a research perspective in order to pay off with operational perspectives in the longer term. I think there are things that we need to be identifying now to begin as research projects, or to emphasize as research projects that we expect to reap benefits in the 5 to 10 year time frame that don't necessarily show up right now, but we nevertheless need to invest in. So, having sort of a communications cycle between the operational side and the research side is critical, and this is what things like EPIC are supposed to address.
Yeah, I guess I see also that opportunity is that when you look at developing a strategic plan, a longer-term strategic plan. So if NOAA were to say we're going to, do a 10-year plan, and they have, but there isn't always the parties in the room are not, operations and research together formulate so we have common goals. Typically, what you see at other centers has been research is helping to drive the direction, and operations is helping to focus the direction so that it meets what are relevant goals that are meaningful. That operations needs to make sure it stays relevant. Research needs to be able to provide the different tools or opportunities or suggest places where directions can go to provide benefit. So you need both, and the conversation needs to be together. And I guess that's my hope, is that we can move towards a common goal where some of these research activities and operational requirements come together. All right, thank you everybody for coming.
What is your schedule for the rest of the day?
I'm open right now.
Okay.
Beers later.
Okay.